Welcome today to our Blockchain Commons Gordian meeting for June of 2025. Uh, my name is Christopher Allen, and as we always do, we explain what is Blockchain Commons. We're a community interested in the self-sovereign control of digital assets. We bring together stakeholders to collaboratively develop interoperable infrastructure. We design decentralized solutions where everyone wins, and we are a neutral not-for-profit to enable people to control their own digital destiny. Today, we're going to be talking about provenance marks with a special presentation by our lead researcher, Wolf McNally. Wolf, go ahead.
Great, thank you. I'm Wolf McNally, your lead researcher for Blockchain Commons, and I will be presenting on something called provenance marks, which let's see, I'm going to share my screen here. Okay, you should be seeing my slides now.
Yes.
Great. Okay, so I've been looking forward to this for quite a while. So let's dive in. So the source for this primarily is going to be the white paper. It's in our Blockchain Commons Research. That's what BCR stands for, repository. The paper is called Provenance Marks, an Innovative Approach for Authenticity Verification. It has this very long URL at GitHub, but if you go to https provemark.com, that will redirect you right to that white paper. So I want to start with the proposition of what creates value. And I argue that two things combined create value: scarcity and provenance. And I'm going to talk about both of those and how that matters to people who care about digital sovereignty, which is the mission of Blockchain Commons. So first of all, we have to ask, what is value? And I would say that value is that which induces people to trade, that is, to give up other things of value. And value is created by the intersection of scarcity, which is a limited supply, and provenance, which is verifiable authenticity. You can also think of this as reputation. So when you have neither scarcity nor provenance, you have very common goods like ambient air that we all breathe, tap water, mass-generated AI images. Now, obviously, there's a certain amount of provenance to tap water. It comes from, government supplies and all that. So it's not that you never know the provenance of anything, but when you don't care, then it's equivalent to not having any actual provenance to the object. Mass-generated AI images, some of them are getting so good you don't know whether they're fake or not. But if you don't know where they came from, then you have no reason to trust them. So what happens when you have provenance but no scarcity? Well, then you have things like cryptographically signed Linux ISOs, Creative Commons licensed art, or Google fonts. These things all have clear provenance. That means we know where they came from. We know who created them or licensed them, who owns the copyright in them, or who manages their license structure. But they're not scarce. They're available to everyone to use freely under the terms of their very broad licenses. What happens when you have scarcity but no provenance? Well, again, scarcity is defined by people's perception, but provenance is basically reputation. And some people try to play off of reputation to create a form of scarcity when there is really no good provenance. And this would include things like counterfeit handbags or other luxury goods, forged artwork, or ungraded trading cards, things like that, where there's an impression of scarcity when somebody offers these things to you, but there really is no reliable provenance to establish that reputation. And finally, we have objects where there's scarcity and provenance, like certified organic produce with traceability, authentic luxury goods with serial numbers, museum-grade artwork with a chain of custody, and even Bitcoin, which includes a fixed supply and a public ledger. And both of these things give you scarcity, which was unusual in digital goods before Bitcoin showed us how, and provenance, which is the public ledger. We know where it all came from, or when it was mined, and the chain of custody that the digital objects have passed through. So I want to ask this question, and I'll come back to it later. When bits are never scarce, how does establishing provenance help creators manage scarcity? So obviously, digital sovereignty involves having some control over what you create, but as I say, without scarcity, there's no value. Without provenance, there's no value. That is, you can't induce people to trade for it. So I'll be examining this more later. So now I want to introduce provenance marks. Provenance marks you can think of as smart serial numbers. They're usable for physical or digital works, so you can put them on a painting or a podcast. They establish an object's originating entity, which is not the same thing as current ownership, which, for example, an NFT, somebody can prove they own an NFT, that's current ownership. But we're talking about originating entity, which is different. They situate a work of some kind in a time sequence stream of works, and they can prove that a work has been unaltered. They can also provide any other metadata you care to associate with the work. So what are the basic requirements for provenance marks? They need to be globally unique. They need to have negligible cost to generate and verify. They need to be small and easy to handle. They need to be flexible and extensible. They need to be non-repudiable. That means once you issue a provenance mark and it's out there, you can't basically take it back or change it. And it's easy for small creators to pick up and use. And this is actually really important to the design. You'll see some aspects of that design a little bit later. But it also needs to be scalable to industrial applications like chain of custody, supply chains, things like that. Importantly, my goal was to have no or as little infrastructure as possible to make provenance marks a success. So no public key, no signatures, no certification authority to issue keys or certificates, no global ledgers, and no expensive consensus algorithms. And I know that seems like a tall order, but I think you'll see that I do deliver on it. So what preconditions do you have to make a system like this work? Well, you have to have a private cryptographic seed, which is held by the originating entity. Notice I say originating entity and not author or artist or creator, because it could be anything that actually holds the seed and issues the marks. This seed carries the same protection concerns as any private key. So you have to protect it. You have to back it up in a way that is not going to leak. And you have to have the originator's publicly published chain of marks. And by publicly published, obviously the blockchain is published. It's secured worldwide through a huge network of miners that spend a huge amount of computing resources on it. But what we want is something that works from a very grassroots level up. So this can be a sole source publication. And in fact, my example is my own Provenance Mark chain, which is a GitHub gist. And you can see that right now by going to provemark.com/wolf. And you'll see it's just a list of provenance marks with its metadata. But the more widely published and copied, the better. And why is that? Well, it's because if you have many copies of a provenance mark chain, you can cross-check that and make sure that, for example, I or another originating entity hasn't tried to take back or alter their chain. So I'm not going to go deeply into this slide, but there are some other systems out there like cryptographic event logs, or CEL, from the W3C, and the Coalition for Content Provenance and Authenticity, the C2PA. Cryptographic event logs are intended to be used for supply chain and chain of custody, and various kinds of updates to state of complex systems. C2PA is primarily intended for use with media like news video footage, camera photographs, and things like that, so that you can see how they've been altered. Provenance marks are, in some ways, much more of a simple building block. You could build either of those two systems out of provenance marks, but because provenance marks have a very low barrier to entry, I think they could be used for a lot more. So let's talk for a moment about provenance marks and decentralized identity, because there's some other initiatives out there that provenance marks can support. Provenance marks are a self-sovereign trust anchor. They enable, DID stands for distributed identifier. They can enable DID URIs without reliance on external authorities or global ledgers. They provide forward linked hash chains. We'll talk more about that in a moment. that ensure tamper-evident continuity across DID document versions, and we're actually using this for our own XID or ZID documents. They support simple revocation and rotation, so you can, if your seed becomes compromised, you can actually rotate it. Lightweight, non-repudiable cryptography, which we talked about before. Uses a single private seed, no signatures, public keys, or consensus needed, which I mentioned before. And uses efficient O of 1 hash verification, ideal for mobile and low resource environments. So you don't need mining, proof of work, proof of stake. You can use them with flexible decentralized storage. Provenance chains can live in Git, as you'll see with my Provenance Mark chain as a GitHub gist, IPFS or social media. And because SHA-256 is actually pre-image resistant to quantum attack, you don't need to replace the algorithm when quantum computing becomes a serious threat. All right, so how do provenance marks work? I've made some big promises. Let's talk about the actual mechanics now. So the core concept is the forward hash chain. So each mark in the chain links itself into the chain by revealing a secret key that was pre-committed to in the previous mark. And a mark pre-commits to the still secret next key by publishing the hash, which includes in its image, that is the source of data that goes into the hash, the next key and other data from the current mark. So what does that look like? So if we have provenance mark 1, which includes its key 1, then that key is the last piece of the puzzle needed to unlock the hash that was published in the previous mark, mark 0. So the hash basically is a promise that the next mark will reveal the key that lets anybody easily recompute the hash. At the same time, mark 1 publishes the next hash in the chain, hash 2. So when mark 2 is published, it includes key 2, which again lets anybody verify that key 2 is the missing piece for hash 2, meaning the person who generated this must have the seed of the original that started the whole chain. And this just continues on for every mark in the chain. So the forward hash chain has a long conceptual lineage. It's not a completely original idea. Most systems you find, like cryptic event logs and C2P and so on, they link backwards. They include every new object includes a hash of the previous object, Provenance Marks does it the other way around, but it's not a completely original and untested idea. And I'm not going to go into each item here, but if you want to investigate these, you'll see that there are a number of other successful proven systems that use this concept, but never quite in this way. So the core mechanism that allows provenance marks to work is a pseudo-random number generator, or PRNG. True random number generators generate a stream of randomness that's impossible to predict. PRNGs generate a stream of randomness that is also impossible for people to predict who do not have the seed that generated the random number generator, but is entirely predictable by somebody who does. So the purpose is to generate the sequence of keys that is deterministic and hard for attackers to predict. Provenance marks use an algorithm called Zoshiro 256 star, which was chosen for its speed, portability, and statistical quality. It's actually a very simple algorithm, but it's been very well tested to produce a stream of numbers that's indistinguishable from truly random, even though it's deterministic. You may be aware that certain random number generators are considered cryptographically strong because they don't use a seed internally. They use some kind of source of system entropy or randomness that basically makes them kind of worthy of cryptographic techniques. Well, we don't need that in this case because we want a deterministic sequence, but we do want a sequence that looks statistically random. So the originator holds a secret 32-byte seed that is generated using a crypto quality RNG. And optionally, the current pseudo-random number generator state. And this is so that this makes the generator of the next key O of 1 complexity. So if you want to generate the nth key and you have the current random number generator state, you only have to use one computation to do it. Whereas if you only have the seed, you have to use n computations to generate the nth key. So what do provenance marks actually look like? They are a binary structure with 5 mandatory fixed length ordered fields. The first one is the key, which we've already talked about. It's the current output of the PRNG, some number of bytes from the PRNG. The second is the hash, which is the SHA-256 of the next mark's PRNG output and the other fields of this mark. The ID is a unique identifier for this chain. The sequence number is a monotonically increasing sequence of numbers from 0, 1, 2, 3 that basically order the chain. And the date is a date stamp, the date of the mark generation. Now, the date always has to be at least as high as or at least as recent as the previous mark. It can never go down. It can only stay the same or go up. And a provenance mark may include an optional sixth variable length field at the end called the info field. And this is the info field consists of DC-bore data of any kind embedded in the mark. So now I've just thrown the term DC-bore, and if you're familiar with blockchain commons work, you might be familiar with DC-bore, but let's take a moment to discuss it. DC-bore is conformant CBOR. CBOR is an IETF RFC 8949, which essentially you can think of as like JSON but binary. So all DC-bore is conformant CBOR, but it has a few restrictions, and we consider these best practices, especially where determinism is concerned, which is important for cryptography. So numeric values all have to be encoded in their shortest form. Floating point values that can be encoded as integers must be. No nans are not a numbers with payloads, and I didn't even know that nans had payloads until we got deeply into this. Probably most people who even know what nans are don't know that. Map keys, you can think of maps as hashes or dictionaries, have to be sorted with no duplicates. No indefinite length types, which is a feature of CBOR that's great for streaming applications, but we're not using streaming applications in this case. And only the simple values true, false, and null are allowed. So there's quite a few other allocated simple values that don't have meanings in CBOR, and we're basically excluding those. And finally, strings have to be in Unicode normalization form C. And this is essentially meaning that any string you encode that has foreign characters or whatever, there's one specific way it has to be encoded, and this is a very standard way of doing things. So this is specified in the IETF draft McNally deterministic CBOR, which anybody can look up. And we have reference implementations in Rust and Swift. And there's also third-party implementations available. Okay, so finishing up that DCBOR sidebar, back to provenance marks. The Genesis mark is the first mark, and it establishes the basis of trust for the chain. It defines what three fields have to be. The key has to be the first bytes of the output of the PRNG after it's been seeded. The ID has to be the same as the key, which basically means it's also random, but it's fixed for the whole chain. That means you can't choose your chain's ID. The sequence number has to be 0. That means that the Genesis mark of a chain can be recognized by the key being equal to the ID and the sequence number being 0. So resolution, I mentioned that there's a certain number of bytes allocated to these fields. Well, you can choose the number of bytes allocated to these fields, but you can only do it on a chain-by-chain basis. You can't do it on a mark-by-mark basis. And this is called the chain's resolution. There's 4 resolutions: low, medium, quartile, and high. And as you can see, they all have different sizes, with the lowest one being only 16 bytes. So you can actually use provenance marks successfully with only 16 bytes per mark. And this would be good for things like physical objects, like sculpture or paintings or things like that. And also where you feel like the security risk is low, where there's not much need for hackers to use advanced computing resources to attack it. At the other end is the high, which is 106 bytes, which is basically industrial strength, could be used for anything, is basically considered to be unbreakable by any attacker. The hash itself is formed by concatenating these 6 fields you see: the key, the next key, which is the generator's output for the next mark, which you don't reveal at this point, the ID, the sequence number, the date, and the info. And then you truncate that SHA-256 image to the what's called link lane, which is link length, which you can see is only 4 bytes for low, and but you don't truncate it at all for high, which is 32 bytes. Also, anything in the info, as you can see, that's concatenated at the end, becomes bound to the mark. So the actual hash of the mark includes the info that's been attached in this mark. The date itself, I won't spend a lot of time on this, but at low resolution, you only have 16 bits, so you have 1-day accuracy. At the quartile and high resolutions, you have 48 bits, which give you 1 millisecond accuracy for thousands of years. Finally, there's three fields, ID, sequence number, and date, which are either unchanging, like ID, or kind of obviously incrementing, like the sequence number, or the date. And we basically would prefer that all of these fields, the entire provenance mark, look like random data. And so we go through one final step when we serialize it called obfuscation, where we run the payload fields through the cha-cha-20 cipher, which is not intended to be actual encryption. So we call obfuscation because it's entirely reversible using the key, which is the header, as the symmetric key for the cipher. But it's very important that humans be able to identify provenance marks at a glance. So we have a number of mechanisms to do this. So since each provenance mark is globally unique but statistically random, humans need quick ways to distinguish between and search for unique digital objects like marks. And we've used these techniques in a few of our other techniques like cryptographic seeds. So for example, as you can see, the entire provenance mark is outlined there. And you can run that through into an algorithm like lifehash, which you can look at lifehash.info. This is another open source algorithm from Blockchain Commons that takes any digital input and produces a beautiful and unique fingerprint using Conway's Game of Life. And this is, as you can see, there's three examples there. And so that can be used to identify a mark at a glance. Also, you could take the first four bytes of the hash and use that as a 32-bit identifier that's unique for every mark. And you can convert that to certain human-friendly forms that you can even put in a tweet. For example, you can use byte words. In this case, we're using the Unicode character circle, solid circle P to precede this, to say this is a provenance mark identifier. It's not the full provenance mark, but you can see these four words are from a set of 256 curated words called byte words. We'll talk about those more in a bit, but they're basically guaranteed to be unique for each byte value. So this is each showing these 4 bytes of the hash. We also have a curated series of 256 emojis called bytemojis. And in some contexts, less formal contexts, you might want to just use these. And since these are essentially also text, they can be used as search keys. So let's look at some examples of provenance marks in the wild. And since so far I'm the only person publishing them, and we're looking forward to that day when arrives when somebody else will also be publishing provenance marks in hopefully the not too distant future. So I'm going to show some examples. This one is just a bumper sticker. Basically, I came up with. I did a text poster of it, and I posted it to X. But you notice at the top above the poster there is a provenance mark identifier, and it's these 4 emoji. And if you actually go to my provenance mark chain, the URL I gave you before, which is provemark.com/wolf, and search for that, it will take you immediately to the entry, which basically says that here's a summary of the post and a link back to the original post. The UR:"provenance" is the full mark, including the key, the chain, the sequence number, the chain ID, the sequence number, and so on, the date, and obviously the things below it are derived from it. The comment you see below it, "as if beauty is real," because it is not part of the info field. In fact, none of these marks on my chain are currently using the info field, which means I could edit this if I wanted to, but I cannot change the actual sequence of marks. So for a second example, this is a piece of AI-generated art. If you're familiar with the AI world, and there's a cartoon that was published that looks almost identical, except it was line art, that basically describes how large language models are trained. My observation is that humans also work this way. So I produced this. In this case, the provenance mark is the QR code. And the QR code is a direct link to my gist that actually it just anchors to the actual byte words identifier for the provenance mark. So if you scan this QR code and then went to the link, it would take you directly to that entry. And for a third example, this is another piece of AI artwork that I generated. And let's presume, for example, that somebody sent this to you because they thought it was cute or interesting, but it appears to have no provenance mark on it. There's no QR code, there's no emoji, say it's out of context from where it was posted originally. In this case, the artist, me, actually embedded the identifier in the labels of the file drawers. And you can see there's four words. There's road. There's another word we'll get back to later, and there's cache and navy. The second word is a bit blurry. It could be saga. It could be gaga. It could be some, who knows what it is. But if you know that these are all byte words, then you can figure it out. If we look at the high resolution version I originally uploaded before it was compressed, you see the word is clearly saga. And the thing about byte words is that because there's only 256 of them, they're all four-letter English words. The first four letters are always unique. The last four letters are always unique. And the first and last letters are always unique. And so in this case, since we can clearly make out the AGA part, then there's only one possible byte word this could be, which is saga. So using the full four words, road, saga, cache, navy, and using that as our search key, we can turn this up. Now, obviously, right now we're only searching my gist. In an imagined future, there could be aggregators of provenance mark chains that you could use these as search keys that would basically search, a global database of, millions of provenance mark chains to turn up these unique keys. But what is the tooling as it exists right now? Currently, we have implement Rust and Swift reference implementations. I'm going to focus on the Rust implementation here. And so this is a Rust crate just called Provenance Mark. If you go to crates.io and search for Provenance Mark, it will turn this up. The command line tool itself, um, I could give, if there's interesting Q&A, I can actually give a demo of how this works. I'm going to go through the slide right now, but essentially if you have the Rust toolchain installed, then you can say cargo install Provenance Mark CLI, and then just say Provenance new my chain. My chain is a directory that will be created, and you can see it says Provenance Mark chain created at my chain, and then it immediately writes the Genesis mark, the first mark 0, and it writes that to my chain /marks/mark-0.json, and then it outputs the exact format that you see on my GitHub gist. It's just starting with 3 dashes and ending with a comment. And so all you need to do to start a new gist is you create a new gist and you paste this as your first edit to the provenance mark. From then on, when you want to create a new provenance mark, you say provenance next, and then you can add an optional comment. In this case, the comment is my new work, and you reference the directory. So you can keep track of multiple provenance mark chains because they're each in their own separate directory. And it says mark 1 written to my chain marks mark1.json. And that gives you the next entry that you can edit your gist, copy and paste at the end of your gist. And so that's exactly how I have built up my provenance mark chains at provemark.com/wolf. If we want to look into this a little bit more, if we actually, from the command line, if we print out what is in mark0.json, you see it's basically a parts explosion of the actual provenance mark. It starts out with the UR:"provenance, which is the actual full provenance mark, the byte words and byte emoji identifiers of it, the comment, which is not part of the info field, remember, and then the actual mark as the fields of it broken out. So you can see the sequence number 0, the date on which I generated, the resolution of the mark, which is 2, meaning quartile in this case, the chain ID, the key, and the hash. So there's nothing secret in these JSON files that is printed out. However, there is one other JSON file, which is generator.json, which is the top level of the directory you specify, which includes the resolution of the mark, again, quartile for 2 in this case, the actual seed. That's why this file is secret and needs to be kept secret. The chain ID, which is again the unique ID generated from the hash of the Genesis mark. The next sequence number, which means that we've generated mark 0 and 1, the next sequence number will be 2. And the RNG state. And as I mentioned, by keeping track of the RNG state, you don't have to actually run through the whole list of marks from the seeds to generate the next one. So a little bit about interoperability, because as I mentioned, provenance marks you can think of them as one building block in other much larger potential systems. So first of all, interoperability with CBOR. As I mentioned, provenance marks are a binary structure that has 5 mandatory fixed length fields, which means that provenance marks are not CBOR, where fields are tagged with their length or type in front of them. They're just a binary blob. And if you don't use the info field, you don't need to know anything about CBOR or DCBOR. So there's nothing that intrinsically links provenance marks without the info field to CBOR. But if you want to use the info field for simple objects like cryptographic digests of digital works or descriptive text, it's very trivial because it's like 1 or 2 bytes of CBOR header before the content you want to add to the info field. On the other end of the complexity, you could use a Gordian envelope, which is DCBOR, in the info field as a principal carrier of very complex metadata. And this is what we actually recommend. So provenance marks, although they're binary blobs, are also CBOR friendly. You can encode a provenance mark as a 2-element CBOR array with the resolution, recall 2 means quartile, as the first element of the array, and the binary string of the mark as the second element of the array. We've also registered with IANA the CBOR tag for provenance marks. And that means that when you tag this array with this tag, then provenance marks become self-identifying. You can give somebody the actual encoded CBOR, and they can tell by looking up the tag that this is a provenance mark, and then they can basically understand, and then that in the INR register links back to our provenance mark specification. And then we also keep, since uniform resources or URs are blockchain common spec, we associate the UR type provenance with that tag. And that means all our tooling and your tooling tool, if you use our stack, can encode and decode provenance mark URs. Provenance marks are basically designed to be embedded or to have things embedded in them. So provenance marks can be embedded in any kind of documents. For example, our specification for extensible identifiers or ZID documents can include provenance marks to verify authenticity and ordering of document updates. So as you update your identifier document with various kinds of information, you add the next mark in the chain. And anybody with access to your history of ZIDs can verify that can not only sequence these things in time, but it also can verify that they all came from all these updates came from the same source. Documents can also be embedded in provenance marks, as I mentioned, by using the info field to hold complex structures like Gordian envelopes. So I mentioned the info field a number of times, and it has many potential uses. And these remain to be one of the things that we are working on defining. And we also want to work with other people who want to adopt provenance marks to define uses for the info field. These can include things like counterparty signatures, blind signatures, which are signatures generated by third parties who are asked to sign a hash without knowing what they're signing, digests of and links to claimed objects, trees of third-party works incorporated, adapted, or attributed, this is something that C2PA does, logs of work and chains of custody. And this all feeds back into building the ecosystem, because defining the info field is one thing that we want to engage with various communities who are interested in using provenance marks with. There's a number of other things that need to be done, like building user-friendly apps and tools. Our command line tool is just the tip of the iceberg, and it's still a work in progress. Public registries and verification services for provenance marks. Seed backup and recovery services using protocols like SSKR, which allows social backup and recovery of objects. Integration with existing services, including social media, so people who see digital media can click to verify the provenance mark chain. Public standards for the use of the info field, which is I've already mentioned. And multi-party control of seeds via distributed computation and ZK proofs. And this would basically be so rather than one person holding the seed, no one person holds the seed, but a group of people together hold partial keys that come together to make a seed. So the seed is never actually constructed in a way that can be learned by anybody, but it's used to create the next mark. So I want to come back to the question I asked at the beginning. When bits are never scarce, how does establishing provenance help creators manage scarcity? As I mentioned at the start, provenance marks are about identifying the source of a mark, the source of a work, not ownership, like NFT transfers on a blockchain or whatever. However, provenance marks also can be used for similar techniques, but with very little overhead. So, example, if we have 2 actors, A and B, A may commission some work from B. Now, A in this case is the A colon. I want you to read that as publishes a mark to her chain. So she publishes a mark to her chain saying that she is commissioning a work from B. B then publishes a mark to his chain saying that he accepts the commission from A. B now logs events in his creative process, establishing the value of the work. Now, this is the most important step, which is why I made it bold. And the reason is that because I said scarcity and provenance together create value. Provenance in this case doesn't just mean a provenance chain, but it means especially for creative creators, like whether it's people who make hand goods on Etsy or whatever, to show that they're not creating cheap knockoffs, they need to assiduously document their creative process. Because what I contend is that people, when they buy art, they don't buy art; they buy the artist. They buy the story behind the art. They buy the narrative arc that the artist is telling. And if they want to ensure that it wasn't created using AI tools, for example, or that the artist is operating with integrity, they want to. The part of what they're buying is this record of this journal, essentially, of the creation process. So this may involve B publishing a number of marks that link back to original source materials, sketches, notebooks, whatever. B finally requests payment for finished work from A. And again, this is all being conducted on their provenance mark chains. A pays B for finished work, so you can actually include like payment addresses or whatever inside provenance marks. B then assigns the ownership of the finished work to A. And this is all being done without direct using blockchains or NFTs or anything like that. A then receives the ownership of work from B. So now there's been a handshake on their provenance mark chains that can be verified by third parties. At a later time, A can transfer ownership to another party, and now because it's all public, other parties as well also have access to the entire provenance mark chains. And C receives ownership of the work from A. So what we've done here is we basically created ownership, that is scarcity, of a digital good while keeping everything public. So there's a number of other topics discussed in the white paper that we haven't had time for here, which include a deeper security analysis of the four resolutions, increasing security using what I call heartbeat marks, which is basically publishing a blank mark not associated with any work at a periodic interval to your chain, which actually increases the security of your chain. It's totally optional, but it makes it harder for anybody, including the originator, to insert marks into the chain in the past. How to rotate seeds, either just for general security protocols or because a seed is suspected to be compromised, and analysis of other potential fields of application. That concludes the presentation. I'd be happy to take any questions, or Christopher, you want to offer any closing comments?
Yeah, I just wanted to quickly fit in, where does this fit into the larger Gordian stack? Obviously, tooling wise, it's leveraging envelope and DC bore and all of those types of tools. But what we've run into as we are evolving the stack is that we have some fundamental needs for ordering. But we often don't need, I mean, we could do ordering with Bitcoin, we could do ordering with open timestamps or any one of a number of protocols that are out there. But all of them require you to um, uh, request, pay for, et cetera, services from a variety of different kinds of parties, with that, some of which are decentralized and censorship resistant, some aren't, et cetera. And it just left things out of true self-sovereign control. Um, so this is I think a really good solution that kind of breaks down to what is the sort of absolute minimum that we can use to make some very basic guarantees. I mean, the entity that holds the secret could be a computer, could be some kind of hardware element that generates these. It can be a wide variety of things. We're not saying anything about that party. We're not even necessarily saying they're the creator, but they are the entity that holds the seed. And from that, we can basically say, here is this continuity of revisions of various types of objects, and um, we can know that where we are in the revisions, and then if a year later you receive a new copy of the document, you can go, oh well, it's been revised in this number of ways. Um, but we're not trying to solve classic censorship resistant. I mean, you can think of Bitcoin as being a very expensive censorship resistant protocol. This is sort of at the other extreme, which is, yeah, you could censor these, but they're so ubiquitously easy and available to distribute and whatever the censorship resistance isn't required. So we feel like this is going to be a real complement. If you go back to our previous presentation on ZIDs, which is kind of a DID 3.0 framework, we're planning on using provenance marks to allow you to do peer-to-peer DIDs and peer-to-peer ZIDs, excuse me, and various small group trust metric models where provenance marks are used so that when you receive an update to a document, you can understand that at least with that party that you've trusted for the last year has basically given you some new information, and you can do things. I'll add one more element to this, is that provenance marks, when used in conjunction with envelope, which is optional, you don't have to use envelope with provenance marks. It has a unique advantage that I can provide you something with a provenance mark where I'm actually not revealing all of the information to you now. So I could give you a document that has a wide variety of elided fields, but the provenance mark will be the same when I later reveal a different envelope that has some of those fields unelided. So I think there's some real advantages insofar as privacy. When I was doing some research on say, supply chain issues, there are a lot of issues having to do with the confidentiality of the different parties in the supply chain. They don't want all their competitors to know every detail of their relationships with all these different parties as a particular object moves through, or a part moves through the supply chain. This allows you to elide that information, but it is committed to such that the ecosystem as a whole can see the part moving through the supply chain, get the information they need. Parties like particular vendors who have relationships with other specific privacy confidentiality relationships with other vendors can unelide the things that they need to evaluate the trust as it goes through. And then later, if a court or some other third-party arbitration body basically needs to evaluate something, all the commitments are there. And the provenance marks offer you a very simple, not overly cluttered, not overly complicated, and well proven with over 40 years of cryptographic experience, and as a particular technique. So I hope that gives you kind of a perspective of where it fits into the larger picture.